Welcome to Dart Tutors. Today, we're going to explore a key concept in bivariate statistics for the IB analysis and approaches higher-level curriculum. That concept is the regression line of x against y. This topic is essential for understanding more advanced statistical modeling. By the end of this video, you will be able to determine when it's appropriate to use the regression line of x against y, find its equation using technology, and use it to make predictions. You'll also understand how this line relates to the more common regression line of y against x. Before we dive in, let's quickly review the standard regression line, the regression of y against x. In this model, we're trying to predict a response variable, based on an explanatory variable, x. We use the equation y equals x plus b. The process of finding this line involves minimizing the sum of the squared vertical distances from each data point to the line. These distances, often called residuals, represent the error in our prediction. By minimizing their sum of squares, we find the line of best fit. This model makes a crucial assumption. We consider the x values to be precise, and all the variability or error is associated with the y values. In other words, the response variable is assumed to be the one measured with error. So, when you see a regression line of y against x, remember that it's the result of minimizing these vertical errors. Now, let's consider a different scenario. What if the y values are more precisely measured than the x values? In such cases, it's more appropriate to use the regression line of x against y. Let's look at an example. Imagine a breath testing station. Police use a breathalyzer to estimate a driver's blood alcohol concentration, or BIC. The breathalyzer result, let's call it x, is just an estimate. If the breathalyzer result is high enough, the driver is required to take a blood test. The result of the blood test, let's call it y, is a much more precise and reliable measure of their actual BAC. Here, y is the more precise variable. Therefore, if we wanted to model this relationship with a regression line, we would choose the regression of x against y. Another great example is studying for a test. Let's say x is the time spent studying, and y is the test score. While we might try to measure study time, it's often an approximation. Did the student take a break? Were they distracted? Test scores, however, are usually counted quite precisely. So the key takeaway is this. Always use the regression line of the less precise variable against the more precise variable. If y is more precise, use x against y. Now let's formally define the regression line of x against y. Just as before, our goal is to find a line of best fit. This time, the equation of our line will be x equals my plus c, where x is the subject. Instead of vertical residuals, we minimize the horizontal distances from each point to the line. These horizontal distances represent the error in our less precise x variable. The formula we are minimizing is the sum of these squared horizontal distances. H equals the sum from I equals 1 to n of h sub I squared. This gives us a method for fitting a line when the error is primarily in the x-coordinate. Now, let's address a common misconception. The regression line of x against y is generally not the same as the regression line of y against x. Let's see why. The first line, y equals x plus b, minimizes vertical distances. It's built on the assumption that y is the response variable and x is explanatory. The second line, x equals my plus c, minimizes horizontal distances. It's built on the assumption that x is the response variable and y is explanatory. The key is that the method of minimization is different. One looks at vertical errors, the other at horizontal errors. This difference usually leads to two distinct lines. Imagine pulling a line through data points. If you're trying to pull it as close to the points as possible in a vertical direction, it will end up in a different position than if you pull it as close as possible in a horizontal direction. They are not the same process, and therefore generally yield different results. There is one special case where they are the same, when the data points lie perfectly on a line, in which case the Pearson correlation coefficient R is exactly 1 or 1. For any real-world dataset with some scatter, the lines will be different. This is a crucial point for IB students to understand. Now let's work through an IB-style problem to see this in practice. Here's a question from a textbook. The data below shows the quantity of feed eaten, x kilograms, and the number of eggs laid y in a fortnight for 12 Leghorn chickens. The data is given in a table, and we'll be using a graphic display calculator to work with it. The first part of the question asks us to explain why it would be appropriate to use the regression line of x against y in this case. Let's think about precision. The number of eggs laid y is a count. We can count the eggs exactly, so the y values are precise. The quantity of feed eaten, x, is a measurement in kilograms. All physical measurements have some degree of error or imprecision. The feed might be weighed slightly differently each day, or some might be spilled. Therefore, since the response variable y, the number of eggs, is more precisely measured than the explanatory variable x, the quantity of feed, it is appropriate to use the regression line of x against y. This reasoning, based on the precision of the variables, is crucial for full marks in an IB exam. Now for part B. Find the regression line of x against y. This is a calculator task. The question asks for the regression line of x against y. You must find the line in the form x my plus c. First, enter the data into your calculator. Put the x values, feed, in list 1 and the y values, eggs, in list 2. It's a common mistake to put the explanatory variable in list 1. However, your calculator is designed to output y against x, or a plus bx. So, for x against y, we must trick the calculator. To get x against y, we need to tell the calculator to use x as the y variable and y as the x variable. So, set your explanatory list to L2 and your response list to L1. Then perform a linear regression. The calculator will give an output like this. It uses a for the gradient and b for the intercept. But remember, it's calculating y calculator equals a times x calculator plus b. In our case, the calculator's y calc is our x, and its x calc is our y. So we get x equals 0.14237 times y plus 0.06033. Rounding to 3 significant figures, the regression line of x against y is x is approximately equal to 0.1142i plus 0.0603 kilograms. Finally, part C asks us to use this line for 2 predictions. The regression equation we just found is our prediction model. X equals 0.142i plus 0.0603. For part 1, we need to estimate the quantity of feed, x, required for a dozen eggs. A dozen eggs is 12 eggs, so y equals 12. We substitute e equals 12 into our regression equation. So x is approximately 0.142 times 12 plus 0.0603, which gives us about 1704 kilograms. We round our answer appropriately. For part 2, we need to estimate the number of eggs, y, laid by a hen that ate 1.2 kilograms of feed, so x equals 1.2. This time, we substitute x equals 1.2 into the equation and solve for y. First, subtract 0.0603 from both sides, then divide by 0.142. This gives y as approximately 8.2. Since y is a count of eggs, we must give a whole number answer. Therefore, we would expect the hen to lay about 8 eggs. These 2 calculations show how to use the regression equation for both forward and reverse predictions. Now, let's tackle a more conceptual problem often found in IB/HL exams. We're given the equations for both regression lines. Y against x is y equals ax plus b, and x against y is x equals my plus c. The first part is to show that the product of the gradients, ma, is equal to r squared, where r is Pearson's product moment correlation coefficient. We'll use the formulas for the gradients. Let's xy be the covariance, x2 the variance of x, and syl2 the variance of y. The gradient of y against x is a, which is covariance divided by variance of x. The gradient of x against y is m, which is covariance divided by variance of y. And Pearson's r is covariance divided by the product of the standard deviations. Now let's compute the product ma. We multiply the 2 gradient formulas together. The sxy in the numerator of a and the sy2 in the denominator of m can be simplified by dividing the top and bottom of the expression by sy2. The expression in the parentheses is exactly the formula for r. So, we've successfully shown that the product of the 2 gradients is equal to the square of Pearson's correlation coefficient. Let's move to the second part of that conceptual problem. The question asks for the conditions under which the 2 regression lines are the same. In other words, when is y equals x plus b identical to y equals 1 over m times x minus c over m? For the lines to be identical, they must have the same gradient and the same y-intercept. Let's start with the gradients. We must have a equal to 1 over m. This means m times a must be 1. From part A, we know that ma equals r squared. So our condition becomes r squared equals 1. This is a profound result. The two regression lines are the same if and only if the absolute value of the correlation coefficient is 1. What does r equals plus or minus 1 mean? It means all the data points lie perfectly on a straight line. There is no scatter at all. In this perfect noise-free scenario, there are no errors to minimize, so both methods of regression yield the same unique line. So we've seen that the regression line of x against y is a powerful tool for modeling data where the y variable is more precise. We learned that the key rule is to always regress the less precise variable against the more precise one. We also saw that finding the equation is a calculator task, but you must be careful to swap the lists to get x equals my plus c. We used the line to make predictions by substituting a known value and solving for the unknown. And finally, we understood that the two regression lines are generally different, except in the rare case of perfect correlation. To solidify your understanding, here are 5 practice questions in the style of the IB exam. Pause the video and try them on your own before watching the solutions. Question 1 asks why x against y is appropriate for time spent studying and test scores. Question 2 gives you a dataset and asks for the regression line of y against x and x against y. Question 3 is a theoretical proof. Question 4 involves a real-world example of distance and travel time. Question 5 is a data analysis problem involving coffee sales and price. Welcome back. Let's go through the solutions. Question 1. Explain why a regression line of x against y might be appropriate for time spent studying x and test score. Test scores are discrete, quantifiable, and exact. For example, a student might score 85 out of 100. Time spent studying, on the other hand, is a continuous variable and can be difficult to measure precisely. Students might estimate their study time, take breaks, or engage in other activities while studying. This introduces error. Since the test score, I, is the more precise variable in study time, x is the less precise one, a regression line of x against y, where x is treated as the response and y as the explanatory variable, would be appropriate. Solution to question 2. Question 2. Given the dataset. Part A, find the regression line of y against x. Enter the data into your calculator with x in L1 and y in L2. Perform a linear regression with explanatory list as L1 and response list as L2. The calculator output gives A and B. Plugging them into y equals x plus b, we get y is approximately 3.32x plus 5.12. Now for part B. Find the regression line of x against y. This time, perform the regression with explanatory list as L2 and response list as L1. We're finding a line of the form x equals my plus c. The output gives us m and c, so the equation is x is approximately 0.2979 minus 1.2. Notice that this is clearly different from the first line. Solution to question 3. We've already covered this in the video, so this is a good opportunity to review the steps. Question 3. Show that ma equals r squared. We start with the formulas for the gradients of the two regression lines and for the Pearson correlation coefficient. We want to show that ma is equal to r squared. Let's substitute the formulas for a and m into the expression ma. The result is SXI squared divided by the product of the variances. We can rearrange this by writing the entire fraction in brackets and squaring it. The expression inside the brackets is, by definition, the Pearson correlation coefficient r. Therefore, ma is equal to r squared. This confirms the relationship between the gradients of the regression lines and the correlation coefficient. Solution to question 4. Question 4. Given data on distance from school, d, and travel time, t. Which regression line should be used to estimate travel time for a student living 15 kilometers away and why? Let's define our variables. Distance from school, d, is the explanatory variable, so we'll use x. Travel time, t, is the response variable we want to estimate, so we'll use y. The question asks to estimate y, travel time, given x, distance. The standard regression line for this purpose is the regression of y against x, or y(x) plus b. This line is chosen because it minimizes the vertical distances, or errors, in the response variable, which is exactly what we are trying to predict. To be thorough, let's also consider the precision of the variables. Distance, x, is a physical measurement and thus has some error. Travel time, y, can also be influenced by many factors like traffic or school start times, and is also an estimate. However, the primary reason for choosing y against x is not necessarily the precision, but the purpose. We want to estimate y based on x. The regression of y against x is designed for this one-way prediction. So, even though both variables might be somewhat imprecise, the purpose of the estimation dictates that we use the regression of y against x. Solution to question 5, our final practice problem. Question 5. A cafe records the price, pieces of a cup of coffee, and the number of cups sold. Explain whether a regression line of S against P or P against S is likely to be more appropriate. Let's first identify the independent and dependent variables in this context. The cafe owner can set the price, P. The number of cups sold, S, then depends on that price. Therefore, price P is the explanatory variable, and number of sales, S, is the response variable. This means we should use a regression of S against P. Let's also consider precision. The price, P, is usually set exactly, for example, $2.50. It's a precise, independent variable. The number of cups sold, S, on a given day, however, can be affected by many other variables besides price, such as the weather, time of day, other events happening nearby, and so on. These other factors introduce error or variability into the S variable. So, from the perspective of both causal direction and the precision of the variables, it is more appropriate to use the regression line of S against P. The resulting line, S equals AP plus B, would allow the cafe owner to predict sales based on the price they set. That brings us to the end of our lesson on the regression line of X against Y. We've seen when to use it, how to find it with a calculator, and its unique properties. This concept is a cornerstone of statistical modeling and a key topic in your IB/AA/HL studies. For more personalized online and home tuition, visit us at Dart Tutors. Thank you for watching.